Okay, so as you recall, in our last class, we were dealing with your area of surfaces. Okay, and where this surface, it was given by the graph of a function of two variables like j equal to f of xy. And we simply started and we just did with one example. And if you recall, I mean, if we are seeking the area of the surface of the graph of this function defined in the domain D in R2, then the area of that surface, it was simply given by what? D, then 1 plus zx squared plus zy squared dA. That's it. That is what we learned, right? So now let us work out this example. So you can see it is about finding the area of the part of the paraboloid z equal to x squared plus y squared that lies under the plane z equal to 9. Okay, so the situation will be something like this. This. X, Y, okay, and suppose this is the paraboloid, okay. This is the paraboloid, I mean, given by z equal to x squared plus y squared, and then we have to find out the area of this surface, which I mean that lies under the plane z equal to 9. So suppose this is 9, so we have to simply find whatever lies below this plane. It is z equal to 9 here. Okay, fine. So now here you can see that if we want to see what is the projection of this paraboloid, of course, I am considering this paraboloid only up to z equal to 9. Okay, so then you will see that this will be this circular disc. This will be this circular disc, isn't it? This will be this circular disc. Okay, this circular disc, and the equation of this circular disc will be x squared plus y squared equal to
9.
Okay, so now basically what we have been given, z equal to x squared plus y squared. Okay, so you know that x equal to 2x and zy equal to 2y. Okay, so then if we have to find out this area, we have to find out the surface area to be precise from this formula. So this is simply going to give me, 1 plus eventually 4 x squared plus y squared dA. 4x squared plus y squared dA. Okay, so now see, I could have considered this domain. So now this becomes my D. Okay, so now I could have expressed this domain in terms of Cartesian coordinates, but rather than thinking it in terms of Cartesian coordinates, if we convert it into polar coordinates, my integration is going to be easier. Okay, so for that, if I convert it into polar coordinates, so then what this is going to give me, this is going to be simply 1 plus 4r squared, right? Then r dr d theta, okay, and then theta is going to go from 0 to 2 pi, and r will go from 0 to 3. Okay, fine. And you can easily evaluate this. So I'm not going to work it out. So I'm leaving it as a homework. Okay, is it okay? Fine. Okay. So this was about areas of surfaces. areas of surfaces. So now what we are going to do, we are going to move to, I mean, see, we were still dealing with multiple integrals. So far we have considered, I mean, multiple integral of a function of two variables. Okay, so now we are going to move to multiple integral. This is going to be related to a function of three variables. Okay, so now, so those are going to be called your triple integrals. So now let us deal with triple integrals. So I'm going to move a bit quickly about this because the underlying concepts we have already learned from, I mean, double integrals. So now we will be moving to triple integrals. We will be moving to triple integrals. Okay. And again, as in double integral, what happened? We were considering a function of two variables, in a domain D. And you have seen that in order to perform the double integration, what happens? Everything boils down to defining this I mean region of integration accurately. Is it okay? Fine. So similar is going to be the case with triple integral. So obviously for a function of three variables, we are going to consider some region belonging to R3. So this region, it is going to consist of points like x, y, z, and this x, y, z, I mean, they are going to lie somewhere. Okay, fine. And that somewhere, the easiest thing is that if we allow them to lie in some intervals. Okay, so that means if we consider this region E to be a rectangular box, that is going to constitute the simplest case. So let us start with this. So let us consider a region in 3D, three-dimensional space, which is nothing but a rectangular box, and it is defined simply by x lying between A to B, y lying between C to D, and say z lying between R and S. Okay. So then, what is going to happen here? I mean, the triple integral. It is going to be. I mean, written as of a function of three variables. Of course, the f is defined over the region E, and then it is going to be denoted by this symbol. I'm going to describe what dV represents. Okay, so V, in fact, V stands for volume. Why it is so? I'm going to tell you. Okay, so like in 2D, so what we are going to do, and here again see the function of three variables. The graph of this. I mean, you cannot visualize it. Whereas graph of a function of two variables, you could have easily visualized it as a surface. So here, what we are going to do, we are going to consider a rectangular box, and whose dimensions have already been given. Then, as before, so we are going to, we are going to divide the interval AB, CD, and RS into sub-intervals, right? Maybe, I mean, n number of intervals. Okay. So then, what we are going to do? I mean, then we are going to get some grid like this. Isn't it? Right? And from there, I am going to choose a small rectangular box. And we are going to assume that this box has dimension delta x, delta y, delta z, and as before, I am going to consider a sample point. Say x ijk star, y ijk star, z ijk star, lying there, and then I am going to construct a sum. Okay, and that sum, it is going to be a Riemann sum. Okay, And then what we are going to do, the upper and lower limit of the sum, what we are going to do, the upper limits, we are going to let them tend to infinity, and that is going to define the triple integral. That's it. Because you are already, quite conversant with, double integral defined in this way. Okay, and once that is accomplished, what we are going to do, we are going to move to different kind of regions, E, because you know that E can be of any shape. It is not necessarily of the shape of a rectangular box. Okay, so how to deal with those kind of shapes, that we are going to learn. Okay, fine. So let us just quickly browse through the slides, and then I'll come back to those arbitrarily shaped domains. Okay, so this is about your triple integrals. This is about triple integrals. Okay, so here what we are doing, we are considering a rectangular box B. I have already told about the dimension of this box. So then, as before, what we are going to do, by simply dividing those intervals in which x, y, and z lies. Okay, so we are going to subdivide the rectangular box into some small boxes. Okay, and see, it is going to be something like this. And if we consider a very, this is going to be an elementary box that we are considering here, and it has dimensions delta x, delta y, and delta z. Okay, and this box I am going to denote it by Bij. Okay, so this is as I have told you. Let us first deal with the simplest case where f is defined as a rectangular box, and this box is defined as this. Okay, and then what we do, the first step is to divide B into subboxes. We do this by dividing the interval AB into L subintervals like this. And again, as I have told you, you can consider each of those subintervals to be equal length, or even if it is not of equal length also, it is going to work. You don't need to worry about it. Okay, so similarly, CP into F subintervals and RS into N subintervals. Of course, they have, each subintervals have weights, delta x, delta y, and delta j respectively. And the plans to the endpoints of these subintervals parallel to the coordinate plans divide the box into element subboxes. It's pretty straightforward to understand. And the subboxes will be like what? Bij, and they are going to be defined as this. Okay. So now you know that the volume of this subbox, it is going to be given by simply delta x, delta y into delta z. Okay, fine. So then what we do, we simply form the triple Riemann sum. It is given by this, as I have told you. So x is a k star, comma y is a k star, and z is a k star. This is nothing but a sample point. Okay, in that box Bij. So again, by analogy with the definition of the double integral, what we do, we define a triple integral as the limit of the Riemann sum. This limit of the Riemann sum. This, and of course, if at all this limit exists, so then this is called the triple integral of f over the box B. Okay, fine. And as before, we have Fubini's theorem here also. And again, you know that as we let limit m tends to infinity, we don't have to worry about the sample point line in the box. What we can do, we can consider the value of the function at the point xi, yj, jk itself. That is one of the corner points of the rectangular box. Okay, fine. And this is what defines the triple integral. Okay, so this is the way triple integral is written. Okay, so you have triple integral sign, and then this is the region B. This is the function, and this is dp. Okay, and again, by Fubini's theorem, if f is continuous on the rectangular box, so this you can easily write as simply dx, dy, dz, and we can simply write the limits of x, y, and z over this integration sign as this. So this is as straightforward as this. Okay. So now, next thing what we are going to do, we are going to consider triple integral over general bounded region. Okay, triple integrals over general bounded region. So what I'm going to do, I'm going to explain a particular type of regions, and then you will be able to see that which knowledge I will gather from this, we will be able to handle any kind of region later on. Okay. So what I'm going to do, so it is about triple integral over your general bounded region. Okay, so if you recall for double integral, so those general regions which were lying in xy plane, we consider them to be type 1, and of course we used Roman script in order to describe those. So we have two types of region, type 1 and type 2. Okay, and with the help of them, what we did, well, I explained it to you that any region, any bounded region, it can be expressed as union of either type 1, type 2, or both of those types of regions. So here again we are going to have three different types of regions, and we are going to designate as type 1, 2, 3. So we are not going to use Roman, we are simply going to use this Arabic notation. Okay, so how you describe this type 1, type 2, and type 3 in 3D? So let us first deal with type 1 region. So type 1 region, it will be such that, see, so if that region E, I describe it as a set of points, of course, lying in R3. In most books, they are not going to write as this. So it will be such that your xy, it is going to lie in some domain D. Of course, this is a bounded domain, D in R2, and your J, it is going to be bounded by two surfaces given by maybe U1 xy and U2 xy. Okay, and the situation is going to be like this. Okay, say suppose this is my domain D. This is my domain D in xy, and of course, it is a bounded domain. So then what I'm doing here, say suppose this is one surface, and so basically I am considering this shaded blue domain. Okay, shaded blue domain, and these are the two surfaces. So this surface is, maybe J equal to U1 xy. Okay, and this surface is J equal to U2 xy. Is it okay? Fine. So this blue shaded region, that is nothing but E, and these type of regions are called type 1 region. Okay, fine. So now here, one thing you have to see is that what we are going to do. So now it is about performing this integration, isn't it? It is about performing the integration. Just hold on for a second. Just give me a second. Class हो गया सब बंदा पर. Sorry about that. So, is the board visible, or you want like? Am I audible?
Yes, you are audible.
And is the board visible? Because I have like.
Yes, it is visible.
Okay, I'll still open the window. Sorry about that. Okay, fine. So now, what we will have to do, we have to evaluate this integral, right? We have to evaluate this integral. So now, how to go about it? So if E is the type 1 region, then what we are going to do, we are going to perform the integration like this. So firstly, what we are going to do, this f of xyj, we are going to integrate with respect to z, okay? Where your z is going to lie between this surface. So basically z will be bounded by these two surfaces, okay? So then you know that once you perform this integration, this integration, so then eventually this is going to lead you to a function of two variables x and y, right? So then I'm simply going to write it as this, because eventually this is this whole thing, it is going to look like something like phi of xy, which is a function of two variables, right? So then we are going to integrate this function in the region D. Is it okay? Fine. So now
Yes.
you know that if you want to perform integrate, if you want to, integrate phi of xy over this region. So whatever type of region D is, it has to be bounded, and you can easily perform integration, isn't it? If it is type 1 or type 2 in 2D, then it is straightforward. If it is not, then what you are going to do? You are going to simply convert them into union of type 2 or type 2 regions, right? And then you can easily perform the integration. So this is the way we are going to deal with your type 1 region, okay? So then, again, I'm going to show you some slides. Here. So this we have already explained. So this is type 1 region, as I have told you. This is the case, and as I have told you, this is the way we are going to perform integration. Okay. So now let us see. What happens if D is a type 1 region? Okay. So then what is going to happen? Like say it is going to have fixed limit for x, and for y it is going to be bounded by two curves, g1x and g2x, right? So then my situation is going to be something like this. Is it okay? See, x lies between a and b, y lies between those two surfaces. Then my order of integration is going to be like this: dz, dy, dx. On the other hand, again, if this region D is of type 2 in 2D, so then order of integration will be dz, dx, and dy. You know that, right? So then it is going to be, this scenario is going to be something like this. As I have told you, see, it is dz, dx, and dy. Okay, fine. So now let us try to work out this example. So you have to evaluate your this one zdv, where E is the solid tetrahedron bounded by 4 planes: x equal to 0, y equal to 0, z equal to 0, and x plus y plus z equal to 1. So once we deal with this type 1 region in 3D, we will move to type 2 and type 3. Okay, that's what we are going to do. So basically, what you have to do, just a minute. What you have to do, you have to evaluate this dv, where E is the region bounded by x equal to 0, y equal to 0, these planes and this one, these 4 planes. Okay, so the situation is going to be something like this. So I'll be interested in this plan, so you know that this is straightforward. How you can draw this. Okay, so I am considering this tetrahedron. So this plan is x plus y plus z equal to 1. Okay, so 1, 1, 1. Y, J. Okay, so now the region lying inside this tetrahedron. Okay, so now if I want to consider it as a type 1 region, so then what we have to do, and again another thing I forgot to tell you is that the region D, which we are going to consider on XY plane, it is nothing but the projection. It is nothing but the projection of these surfaces which bounds. I mean, J will be bounded by 2 surfaces, right? So it is going to be the projection of those 2 surfaces over your XY plane. Is it okay? Fine. So we will be interested in this D. We'll be interested in this D. Okay, and again, if you look here at this situation, so J is bounded by 1. Here, the J is bounded by these planes, your J equal to 0, and this plane is simply J equal to 1 minus x minus y, isn't it?
Yes.
Is it okay? So now this is my D. If you look at D, if I want to again, D is beautifully shaped. I mean, like this is your D. And it is like this is simply x plus y equal to 1, right? This is 0. This is 1, 1. So either you can consider it as a type 1 or type 2 region. Now, if I want to consider it as a type 1 region in 2D, so then your x is going to be x lies between 0 and 1, and y lies between, this is y equal to 0, and this is y equal to 1 minus x, isn't it? So now, see, as I have told you, it is about expressing that region accurately. So what I have got x lying between 0 and 1, y lying between 0 and 1 minus x, and z lying between 0, 1 minus x minus y. That's it. I need nothing else. So therefore, your this E z dv, this is going to be simply your j going from 0 to 1 minus x minus y, j dz, then dy, y goes from 0 to 1 minus x, okay, and dx, x goes from 0 to 1. Fine? And this can be easily integrated, right? So should I perform the integration or you can do it?
It is okay.
Yeah, I think you can easily do it, right? So this is the way we are going to tackle this. This is the way we are going to tackle this. So likewise, if I consider type 2 reason, if I consider type 2 reason in 3D, so then what it is going to have? First thing we consider xy plane, xy plane for D. Now what I am going to consider? I am going to consider your YZ plane. So your D is going to lie somewhere here. Okay. So your I am going to have a situation like this. I am going to have a situation like this. Okay. So here X is going to be bounded by two surfaces U1 YZ and U2 YZ. Isn't it? In type 2 region. Fine? Okay? Similarly, you can visualize type 3 also. So I am going to show you simply the slides. And again, I mean, according to your convenience, you are going to, make use of, or you are going to convert a region into type 1, type 2, or type 3 region. Okay? Fine? So, let me just quickly have a look at that. So this we have already worked out. So this is the answer. The answer is already, I have already typed it there. Okay. So as I have told you, so type 2 reason it is going to be where the x range, is going to be bounded by two functions of y and j. So then your reason is going to be something like this. And again, you consider D to be a type 1 or type 2 reason in the YZ plane, and you can easily perform integration. So similar in type 3 reason, where that D is going to be considered over XZ plane, okay? And then Y is going to be bounded by, two surfaces, which are nothing but the graphs of functions of XZ. So this is the way we are going to perform integration, right? So I think you can easily do that. So now let us come to one interesting example. So it is about evaluating that. Let me simply write it down, and after that I'll come back to Blackboard. So this is x squared plus z squared dv, and when A is the region bounded by the paraboloid y equal to x squared plus z squared, and the plane y equal to 4, and the plane y equal to 4. Okay, so let us see what this equation is. Okay, so say parabola is, the axis is going to be y-axis. Okay, it is x squared plus z squared. So it is going to be something like this. It is going to be something like this. Okay, your paraboloid is going to be something like this. That is not a very good figure. I can do better. Okay, fine. Yeah. Fine. Okay. So this is the paraboloid, your j equal to x squared plus j squared. Right? Y equal to x squared. Sorry about that. And this is the plane. There's a plane. Which starts the paraboloid. So this is, this is 4. This is y equal to 4. Okay. So now, what is happening out here? If I consider the region E to be a type 1 region, so then what we have to do? We have to consider the projection of this paraboloid over your
Exactly.
no, if it is type 1 region, that is what I'm coming to. I have to consider, see, firstly, let me try to deal with as a type 1 region, right? So then I have to consider a projection over your xy plane. So this will be my D. Okay, so in that case, this is going to be my D. Okay, so in that case, what it is going to be? I will have something like this. In xy plane, yeah, when z equal to 0, it is simply going to be this region, right? It is simply going to be this region. Fine, and this is y equal to 4. Is it okay? Fine. So then what would have happened? So that means my E would have been xyz, and then such that from here what I will get your xy belongs to D, okay, and j goes from if you look at here, so j goes from what, where, your minus square root y minus x squared to plus square root y minus x, okay, and then what is this D? D would have been your xy. If I consider it as a type 1 region again, say. So then what is going to happen? My range of x would have been from -2 to 2, right? -2 to 2. X would have been -2 to 2, and y would have been what is the lower surface? X squared and 4, right? And then the integration, if I now look at the integration, now let us come to that one. X squared plus z squared dz. J goes from y minus y, this. Okay, so then y goes from x squared to 4. Then x goes from -2 to 2. Now, by the look of it itself, I mean, you would be terrified, right? Although, as mathematicians, we know that we will be able to work it out. But the thing is that why go that cumbersome way? Isn't it? Why go that cumbersome way? Because it is not that we only know about type 1 region. We know about type 2 and type 3 region as well. Is it okay? Fine? So, that is why, I mean, rather than trying to accomplish the integration through this cumbersome way, let us think about this E as type 2 or type 3. So what could be the best? Can you tell me?
We should take the xz plane.
Yes, I should take the xz plane. So basically, if I take the projection of this parabola over xz plane, my job will be much more easier. So if I take the projection of this over, xz plane, it is simply going to be this circle. Isn't it?
Yeah.
It is simply going to be this circle. Okay. It is simply going to be this circle. So this is going to be my D. This is going to be my D. So basically, now this is Okay, so
equal to 4.
4. So this is going to be my t. This is going to be my t. Okay, and then how we are going to perform it. So then you know that. Here again, what we'll have to consider? We'll have to consider, I mean, the lower surface and the upper surface, isn't it? We have to consider the lower surface and the upper surface. So now, basically, I'm going to consider it as a type 3 region. Consider it as a type 3 region. So for that, what I'm going to do, so E equal to x, y, z. So such that what I'm going to do, your xz belongs to D, right? And y lies between x squared plus z squared and 4. Okay, right? We are going to deal with that, region, two-dimensional region D later. Okay, so now, so this one, your x squared plus z squared dV over this region A. So what it becomes? It simply becomes D, and then your y goes from x squared plus z squared to 4 this square root dy, and I'm simply going to call it dA. I'm not even bothered about what I'm going to do next. So my next step will be definitely integrating this with respect to y, isn't it? So this is simply going to be, because this is independent of y, so it is going to square root x squared plus z squared and simply y, right? So, and the limit of y is, upper limit is 4 and lower limit is x squared minus z squared. So dA. Okay, and you know that D is a region in xz plan. Is it okay? Fine. So now you know that. Now if I convert D into polar coordinates, my job is going to be much easier, isn't it? So for that, what I'm going to do, I'm going to use x equal to r cos theta and z equal to r sin theta. Okay, so then this is going to convert to what? This is going to convert to what? Your theta is going to go from 0 to 2 pi, and r is going to go from 0 to 2. 0 to 2, and then this is going to be simply r. This is going to be 4 minus r squared, and dA is going to be r dr d theta. Is it okay? Fine. And this is much easier to integrate, isn't it? Is it okay? Fine. So
Yes.
you can easily do that. I mean, the answer is going to be displayed in your slide. Answer is going to be displayed in your slide. So let me again quickly run through the slides. So this is this equation. So this is this equation. Okay, so this is the region of integration. So if you want to consider it as a type 1 region, so you have to consider projection onto xy plane, and that makes it something like this. And as we have already seen, we have already explained that your integration is going to be pretty cumbersome. But on the other hand, if we consider it as a type 3 region, where we are going to consider the projection of this region over your xj plane, so we are going to get a much easier procedure. Okay, so this is the answer. Please try it at home. Okay, and I have a couple of more examples listed here. I have already given you the figures, so you please try it at home. Because your tutorial sheets, they are going to contain a lot of examples, and you'll be able to work them out pretty easily. Okay, so now what we are going to do, we are going to move to, triple integral in polar coordinates. Triple integral in polar coordinates. firstly, we are going to consider, cylindrical polar coordinates. So let me give you a quick picture of. So maybe all of you have already done, cylindrical polar coordinate system, but still, again, it is going to be a revision for some of you. For some of you, you may have learned it quite mechanically. Let me give you a clear picture of what is So now we are going to deal with triple integral in polar coordinates. Okay, so firstly, we are going to deal with cylindrical polar coordinates. Okay, cylindrical polar coordinates. So now, see, when we consider the Cartesian coordinate system, we simply what we do? We simply consider three axes which are orthogonal to each other. Okay, and they meet at the origin O, and we consider a point in space. Okay, so now this point in space, if we consider that the point lies on a surface of a cylinder, so then what happens? So for that, what we are going to do, we are going to draw a perpendicular to the xy plane from the plan, and then we are going to join the foot of the perpendicular. Say, suppose this is L, foot of the perpendicular, and the origin. And suppose the line joining the origin to the foot of perpendicular, it makes an angle theta. With x-axis. Okay, fine. So now I have told you that. Okay, let us imagine that. This point P is lying on the surface of a cylinder. So what about that cylinder? So when we are going to consider the cylinder, so we are going to consider that the cylinder has radius r. Okay. So my situation is going to be something like this. Say, okay, say suppose I am kind of considering giving me a good picture. I think it's not. I think I need to be more careful about it. Just a minute. Okay. So here. So it is going something like this. Okay. So basically, what we are doing, we are considering a cylinder like this. We are considering a cylinder like this. Okay. On the surface of the cylinder, which is of radius r, we are considering the point P. And then, if this is theta, this is r. So then, if we consider xy plane, and if we consider, polar coordinate system there, you know that I can simply write x equal to r cos theta, y equal to r sin theta, isn't it? And simply, these are the transformation formula that is going to be used. So basically, what they are, so you are now considering from xyz system to r theta z system, and this is nothing but the cylindrical polar coordinate system. Okay, so this equation is something like this. Okay, so similarly, if you consider spherical polar coordinates, your situation is going to be different. I'm going to explain that to you later on. But for the time being, let us deal with simply cylindrical polar coordinates, and I'm going to quickly browse through how triple integral is tackled in cylindrical polar coordinates. So these are the different. I mean, see, just a minute. Spherical. Okay, then we set point here. Just a minute. I think I may be in the wrong slide section. Just a minute. I try to get. So this is the thing. Sorry. So this is the thing. Triple integral in, I mean, cylindrical coordinates. So this is the situation we are considering. Okay. So the cylindrical coordinates of a point I have already explained it to you. Okay. So if you consider xy plane, so then z coordinate is going to be 0 here. So this is going to be the situation. And now, if you want to perform an integration in cylindrical polar coordinates, so firstly, again, we are going to consider what a polar cylindrical box like this, okay. And again, if you consider this is a type 1 region, say, so then if we express the region D in xy plane as a polar rectangle, so then you can express or you can describe the region E as this. See, E is xyz such that xy belongs to D, and J, it lies between those two surfaces E1 xy and E2 xy, where D is given in terms of polar coordinates by this. Okay, so where theta lies between alpha and beta, and R lies between those, I mean, two curves given in terms of theta. Okay, so this is the way we are going to do. So then you know that as you perform integration, I mean, with respect to J, I mean, this is going to give you a function of x and y. So then you simply convert x and y into r and theta. Then eventually it is going to lead you to this. And I am not even worried about, I mean, describing how you, like say, through the concept of, I mean, this elementary volume, you can get to this. You may be thinking that I am intentionally avoiding it, but in fact I'm not, because later on, what I'm going to do, I am going to teach you a generalized methodology. Okay, it is about transformation of coordinates, where, I mean, you would be able to tackle any kind of transformation. So, for example, here I talked about how you can transform the Cartesian coordinate system into cylindrical polar coordinate system, right? And I have given you the transformation formulas. So once you know the transformation formula, so there is going to be a we are going to adopt a generalized methodology which will help you to deal with any kind of transformation. Okay, so that is why. So let us simply try to I mean get into this formula mechanically for the time being, and later on I'm going to explain it through transformation of coordinates and concept. Okay, fine. So this is where you have to do. Firstly, you have to integrate. Like with respect to J, and then what you are going to do in xy plane, you are going to convert it into your polar coordinate system. That's it. It's as easy as that. So this is what it is. So x and y, so they have been converted into theta and r, and then we are going to perform integration like this. Okay, and of course you know the I mean range of this alpha and beta. So here beta minus alpha, it is less than equal to 2 pi. Okay, they of course lie between 0 and 2 pi. So this is what it is. So everything is explained. So this is firstly, we are going to convert it into this, and after that, this is going to be a function of two variables, I mean x and y, and then what from there we are going to make use of this fact, and finally we are going to end up with this. This is what. See, now let us think about this example. See, it is about a solid E lies within the cylinder x square plus y square equal to 1. So this is the cylinder x square plus y square equal to 1, and it lies below the plane z equal to 4. This is the plane z equal to 4, and above the paraboloid z equal to 1 minus x square minus y square. So this is the paraboloid. This is the paraboloid. So the density at any point is proportional to its distance from the axis of the cylinder. So find the mass of E. Find the mass of E. So you know that mass is nothing but density into volume. So what we have to do, we have to integrate the density function over the whole region, and the region is the region that lies above this paraboloid, and it lies below the plane z equal to 4, and inside this cylinder x square plus y square equal to 1. Okay, so that is what we are going to do, and then we are going to end today's class with this example. Okay, and before that, I would like to tell you another thing. Okay, just one thing I would like to mention. See, I was talking about this triple integral. So now, one thing I forgot to mention, that if this is a constant function 1, so then it will become simply this, and this simply represents the volume of the region E. So this is simply volume of E. That you have to remember. So now, in my situation here, it is something like this. Okay. So this is z equal to 4 or 9. 4. Z equal to 4, right? Z equal to 4, and then I have this paraboloid. This paraboloid is z equal to 1 minus x square minus y square, and I mean this cylinder is simply x square plus y square equal to 1. Okay, and what has been given to me, this density is proportional to density at any point. So suppose I consider any point of the cylinder. So the density is proportional to its distance from the z-axis. Okay. So now, if you consider any point here, so then if this point is say, I mean, x, y, z, so its distance from z-axis is simply going to be what? Square root x square plus y square.
Yeah.
Isn't it? So it is square root x square plus y square. So that means this is going to be some constant a like this. So if you want to find out the mass is simply this. Mass is simply this. Okay. So that is why what we need to do, we need to simply perform this integration. dV. Okay, so now what is being given here? So now what we are going to do? Firstly, what we are going to do, that let us consider the limits of J. Okay, so then you know that J lies above this surface, and below this plane Z equal to 4. So that surface was what? 1 minus x square minus y square, and that plane is Z equal to 4. And so this is x square plus y square dz, and then dA, dA. Okay, so then what we are going to do, because this is independent of j, this is independent of j, this is going to be x squared plus y squared, and then this is going to be 4 minus 1, that is 3, then minus of x squared plus x squared minus y squared. So this is going to be 3 plus x squared plus y squared, dA. Okay. Now simply for dA, you simply sorry, this is going to be d. This is going to be d. Thank you. So you simply
equation also.
Uh-huh.
In the previous equation also you should write d.
Yeah. This is, sorry, thank you. This is d. This is d. Okay. So this d is nothing but this circle. This is nothing but this circle. X squared plus y squared equals to 1. Right? So simply convert it into polar coordinates, and then this is going to become your theta goes from 0 to 2 pi, r goes from 0 to 1, and then this is simply r. See, this is 3, don't think like this is j. R, and then this is 3 plus r squared, then dA will be replaced by r d. So everything is done. So you can easily integrate it. Okay. So this is one example, and you will find many more examples. So in my next class, what I'm going to do, I am going to quickly deal with, spherical polar coordinates, and again the underlying facts, how you have dealt with that elementary, volume, all these things. I could have explained, but I'm intentionally not going to explain that. Rather than, as I have told you, I'm going to arrive at a generalized formula. Okay, from there you'll be able to tackle anything. So in my next class, hopefully, I'll be able to cover that. So till then I will meet you in my